Okay, so if we look at our rational function section 2.6, we can refresh our memory by going over the fact that domain always refers to our x values, and range always refers to our y values. And we represent the all real numbers with either that double R symbol or with this negative infinity, positive infinity in parentheses. Okay, so we oftentimes get domain and range to be all real numbers, but instead of writing all real numbers, we can use our double R symbol or the negative infinity to infinity. Okay, and this one we call interval notation. So if you ever see something that you need to write in interval notation, you'll use the negative infinity to infinity. Okay, so as I said, we're going to go over functions with domain and range. So we need to graph that function in our graphing calculator. So go ahead and get your graphing calculators out and graph the function 1 over x. Okay, so we should get a function that looks something like this. Okay, that's our 1 over x function. So it's going in each direction. So we need to come up with our domain and range.
Looks like all just everything.
Okay, so for our domain being our x values, I agree that it does look like all real numbers, except that we have one number that it never gets to. It never gets to 0. It never crosses your y-axis. So it's all real numbers, except x cannot equal 0. So if we look at our range, our y values, again, that looks like all real numbers, except it never gets to 0, so y also cannot equal 0. Okay, and so these lines that we did not, that our graph never crossed, those are called asymptotes. So let's look at how we find our vertical and horizontal asymptotes. Okay. So the line x equals a, shut up, is a vertical asymptote of the graph if f of x approaches infinity or f of x approaches negative infinity as x approaches a. Okay, that's called a vertical asymptote. So we saw that on our last graph as being that blue line that I drew. Okay, if the graph has a horizontal asymptote, then the line y equals b is a horizontal asymptote of the graph if f of x approaches b as x approaches infinity or x approaches negative infinity. Okay, so let's look at how we actually find those asymptotes. Okay, so if we're given the function f of x equals n of x, some function, some numerator function, over d of x, some denominator function, then we know, number one, that it has a vertical asymptote when d equals 0, when the denominator equals 0. And that's because we can never divide by 0. Okay? We also know, number two, that it has a horizontal asymptote when your degree of n of x is less than your degree of d of x. And that horizontal asymptote is going to be at y equals 0. Okay? We know that part b of that, if your degree of n of x is equal to your degree of d of x, then you have a horizontal asymptote where your constant of your first function divided by the constant of your second function. Okay, And then lastly, C, we know that we have a horizontal asymptote when your degree of n of x is greater than your degree of d of x, then there's no horizontal asymptote. And these are your leading coefficients. The C1 and C2 are your leading coefficients. Okay, so let's look at our example. F of x equals 2x squared over x squared minus 1. And we want to find our vertical and horizontal asymptotes. Okay, so for the first part of that, we said that we had a vertical asymptote when our denominator was equal to 0. Okay? So my denominator in this problem is x squared minus 1. So I know that I'm going to have vertical asymptotes when x squared minus 1 is equal to 0. Okay, so if we solve that for x, then we add 1. So x squared equals 1. And then if we take the square root of that, then we know that x equals positive and negative 1. So I know that I have vertical asymptotes at positive 1 and a vertical asymptote at negative 1. Okay, the second part of that was finding our horizontal asymptotes. And there were 3 different conditions that we had to look at for our horizontal asymptotes. We had to look at our degrees of our functions. So my degree of my numerator is 2 and the degree of my denominator is 2, and then we had to compare them. And so part B said that if they're equal, then we have a horizontal asymptote where with my leading coefficients, okay? So if I look at my leading coefficients, since my degrees are equal, my leading coefficients are 2 and 1, and my horizontal asymptote was a ratio of coefficient 1 divided by coefficient 2. Okay, and so that's equal to 2 over 1, which is equal to 2. So I know that I have a horizontal asymptote at y equals 2. And if we want to double check those, then let's plug this function into our graphing calculator and see what we get. Okay, so go ahead and plug it into your graphing calculator and let's see what we get. So let's look at what our graph looked like. So everybody should have gotten a graph that looked like this, where this was the line x equals 1. This was the line x equals negative 1. And this was the line y equals 2. Okay, so everybody got a graph that looks something like that? Oh, no? Okay, let me look. You're supposed to put in this 2x squared divided by 1x squared minus 1.
Oh.
So which comma? No? Did you graph it? That is 2 what you got. Yeah? Okay. Kelson, is that what you got? Did you get something that looks like this? Okay. Alright, so let's look at another one where we're going to find our vertical and our horizontal asymptotes. Okay? So if we remember number 1, to find our vertical asymptote, your vertical asymptote is where your denominator is equal to 0. Okay, so x squared minus x minus 6 is our denominator. So our vertical asymptote is going to be where x squared minus x minus 6 is equal to 0.
Factor.
Yep, then factor it. Factors of 6 that subtract to give me negative 1 is 2 minus 3. So I know that x plus 2 and x minus 3 equals 0 are going to be where my asymptotes are, my vertical asymptotes, which tells me then that x equals -2 is my first one, and x equals 3 is my second one. So I have vertical asymptotes at -2 and at +3. Okay, for the second part, to find my horizontal asymptote, I have to compare my degree of my numerator to my degree of my denominator. Okay, so in this case, my degree of my numerator is 2, my degree of my denominator is 2, so they're equal. Okay, and so then, based on my notes, if my degree of my numerator and my degree of my denominator are equal, then I have vertical asymptotes, where my coefficient of my first function divided by the coefficient of my second function. And if I go back up here, that's all I wanted to go. My coefficient of my first function is 1. My coefficient of my second function is 1. And so then that ratio is equal to 1 over 1, which just equals 1, which tells me that I have a horizontal asymptote at y equals 1. So let's graph this function to figure out if that's actually what we get. Where did this go? Yeah, but it's not like, there we go. It's not letting me scroll up. Okay, so go ahead and graph that function and see what we get. Okay, so then we should get a graph that looks something like this, where I have a vertical asymptote at x equals 3. I have a horizontal asymptote at y equals 1. Yes, that's what we got? Perfect. Okay, the last type of asymptote we're going to look at is called a slant asymptote. Okay, and you find your slant asymptote by dividing. Okay, so if n of x, your numerator of your function, is greater than the denominator of your function by exactly 1 degree, then you have a slant asymptote at n of x divided by d of x. Okay, so we don't always get slant asymptotes. We only get them when the denominator of your, when the degree of your numerator is exactly 1 more than the denominator. So let's look at finding our slant asymptote of the function x squared minus x divided by x plus 1. We notice that the degree of my numerator is 2, the degree of my denominator is 1. So this does have a slant asymptote because 2 is exactly 1 more than 1. And we know that our slant asymptote is then when n of x is divided by d of x. Okay, so my numerator is x squared minus x. My denominator is x plus 1. And we're going to do some polynomial long division. Okay, so x goes into x squared, exactly x times x is x squared. 1 times x is positive 1x. Then if I subtract that whole thing, x squared minus x squared cancels. Negative 1x minus 1x is negative 2x. And then we know that x goes into negative 2 exactly negative 2 times. So x times negative 2 is negative 2x. 1 times negative 2 is negative 2. Subtract these. Those cancel. 0 minus negative 2 becomes positive 2. But we don't really care about that. That is our remainder, but what we care about is this up here. So we know that we have a slant asymptote at the function y equals x minus 2. Okay, so that's where our slant asymptote exists. Okay, so let's graph that function and just see what a slant asymptote looks like. Okay, so if we graph this on a standard set of axes, we should get something that looks like that. Kind of a weird shaped graph. And so that line right here, x minus 2, that's our slant asymptote. Okay, so that's what a slant asymptote looks like. It also looks like it might have a vertical asymptote, but we're not worried about that. All we worry about is the slant asymptote. Okay, so let's find our slant asymptote for 7b, where we're looking at x squared minus x minus 2. Okay, so this is my n of x, this is my d of x. So we're going to divide them. So x squared minus x minus 2, and we're dividing it by x minus 1. Okay, well I know that x goes into x squared exactly x times. X times x is x squared. 1 times x is 1x. And we're going to subtract them. Those cancel. Negative x minus a negative becomes a plus. So this becomes 0x minus 2. So we know then that we have, because x goes into 0x exactly 0 times, we know that we have a slant asymptote at the function y equals x. Okay, this negative 2 becomes a remainder, but we don't really worry about that so much. Okay, if you want to verify it, you can graph it in your calculator, or you can just believe me. Okay, let's look at one more. What? Okay. So let's do one more. So we know that this is exactly one more, so we can take my n of x, my numerator, we can divide it by my d of x. So 3x squared plus 1, and we're going to divide that by x. So know that x goes into 3x squared, exactly 3x times. X times 3x is 3x squared. When we subtract those, I get 0. I bring down my 1, so 1 becomes my remainder. And I know that I have a slant asymptote at y equals 3x. Okay, so you guys are going to work through page 191, 31 through 41 odd, 55 through 61 odd. And these are your specific instructions on that, okay? So regardless of what the book says, this is what I want you to do. I want you to A, find your asymptotes, B, plug your function into your graphing calculator to verify that those are your asymptotes, and then 3, sketch a graph. This does not have to be an exact graph. As you notice, like on these ones that I sketched on the board, I didn't put any increments. I just put my axes and I drew sort of what it looks like, okay? So don't spend a lot of time sketching the graph. I want it to be an extremely rough sketch. Okay, does that make sense?